Okay.
Okay, go ahead, Vladimir.
Today I'm gonna present study machine learning methods for pricing financial derivatives by Li Fan and Justin Sirignano. Uh, this study examines machine learning techniques for pricing financial derivatives with a focus on neural network-based methods. They compare these advanced approaches to classical models to determine which better captures real-world market behavior. By harnessing neural networks, they model asset prices dynamically, adapting to patterns that traditional model might overlook. They validate their findings using actual market data, ensuring practical relevance. Um,
So is it like stock market mostly?
it's about pricing of options.
Options, okay.
Uh, Let's begin with the classical models that form the foundation of financial pricing. The Black-Scholes model assumes asset prices move smoothly with constant volatility sigma, uh, making it simple but limited in complex markets. The coefficients R and D here because money loses its value over time and assets can pay dividends.
Mm-hmm.
So S here is a price, uh, R is a risk-free natural rate. It may be like rating in the bank. Uh, D is a dividend rate from stock from underlying asset,
Mm-hmm.
and W is a standard Brownian motion or Wiener process, like the same things. And sigma is constant here. The second model is Houston model, incorporates varying volatility, enabling it to reflect more realistic market fluctuations. It is it describes it is described by a similar stochastic process, but here volatility is a stochastic quantity. You can see that volatility here also uh, is modeled by stochastic process where uh, we have long-term variance, long-term volatility coefficient, and the volatility of the volatility. Like Xi is the volatility of V.
Mm-hmm.
So we just two-dimensional stochastic process where these two Brownian motions have a correlation is equal to rho. Okay. The last one classical model is a local volatility model. Here, volatility sigma is a deterministic function that typically calibrated from market option prices.
So
Uh,
hold on, are you saying that those two Brownian motions are correlated with one another? I mean, I'm trying to understand what this equation two means. The third one in equation two. So
they're correlated, yeah, with
no, like dw, like should I think about the s sub t as a vector, right? Or it's a scalar? It's just one uh, price. And then what does this dot product mean? Is this a dot product of two vectors?
um, it's not like dot. We can assume that it is dot product of two vectors, but it's not about. It's just a notation that these two Brownian motions have a correlation in time.
So it's not they're not independent random variables, you're saying.
Yeah, they're not independent.
Mm-hmm.
Okay. And this model serve in this study as a benchmarks for the neural network model. So consider the following class of neural networks: stochastic differential equation models, the These models describe asset prices and additional factors like volatility using neural network models to define price evaluation over time. Here you can see the two-dimensional stochastic process with different drift terms and volatility terms. All of these terms are modeled by a neural network with at least 4 outputs. And in this paper, they study this type of neural networks as their model.
But do they impose again correlations between DWT and DZT? Oh yeah, you do say the correlation. Yeah, you do.
Yeah, and they also say in study quickly that this row can be also like in theta.
Sure. So basically, you have a stochastic process for whatever price is, and then there is some hidden stochastic process that you don't know about, and then you're just trying to model it.
YT is a latent process capturing additional state information.
Yeah, whatever is not captured by the market. Yeah, I understand.
Okay. To test these models, they use the prices of European options, which can only be exercised at the expiration date. Here you can see the definition. What is European option is it's like when you buy the obligation to buy or sell some assets in the future at maturity time t. We on sell on price k. Okay. So for your opinion option, you can see formulas for payoff function. It's how much you would get if you expire or not expire your option. And for a fixed set of parameters t or parameters theta from neural network, the model generated prices from this stochastic equation would be like in a formula number 5. So you want to evaluate like expectation value of payoff function. And exponent here because money loses value over time. Okay. The first approach that they use is about using mean squared error for loss function. So here you can see it in formula number 6. You have market prices of option of different derivatives like options, and you have the model generated price. And here just loss function of means squared error. Okay, and they say that you can change, you can evaluate model generated price expectation value here using Monte Carlo simulations of stochastic equations. Okay, and here you can see that it's just mean of these simulations. You simulate you simulate prices And then you evaluate the mean of payoff function. So that's all. And the one can use naive stochastic gradient. It is biased because you can see that in formula number 7 and in formula number 8, there's some problem because we use the same Monte Carlo simulations for calculating the gradient of model generate price and the model generate price itself. And generally, expectation value of multiplication is not multiplication of expectation values. And the formula number 7 would be biased. It would be biased estimation. So they use the method when when there are two sets of Monte Carlo simulations. The first one for model generated price and the second one for its derivative. So it would be not biased estimation of gradient. And this gradient is used in stochastic gradient descent, like in other machine learning models. So we generate two sets of Monte Carlo prices, use them to evaluate price, and get model generate price and its derivative. Then calculate gradient and update the parameters of neural network. So we can assume that that generating of paths is some kind of part of neural network architecture. Okay.
So I'm trying to understand. So you're not using gradient descent. You don't use the back propagation. You just have two like proposed sets of trainable parameters, and then you compare
No.
the prediction.
You use gradient descent and backward propagation, but if you use it just in naive way, you would get biased estimation of gradient, and you don't want it. So you calculate differently the derivative of model generated price and the model generate price itself, and use these separate derivatives. You calculate gradient.
I guess I'm just not understanding where the bias is. So maybe you can like
The
go.
bias that
So you have some loss function and that you define in equation 6, right? So and then you can see how that prediction would be adjusted if you change your trainable parameters and that's 7. And you're saying this is not a good, right?
they saying that if you use the formula 6 and take a gradient from this,
Right.
you would get formula 7 because
Yes.
your prices, model generated prices, they are calculated using Monte Carlo simulations, same Monte Carlo simulations.
Mm-hmm.
And you want uh, to expectation value of this gradient would be unbiased estimation of true expectation value of this. But
I see. So you're trying to minimize the expected gradient, not the actual gradient you got. That's the idea.
yeah, yes, of course. Yeah.
Okay. Okay. So you're saying that there is expected gradient, and you should, okay, that makes sense. Yeah, and should minimize that.
Mhm. Yeah, it is expected gradient here
Mhm.
because like model generated prices. Okay. Uh, Here I would just remind you about classical models to
But have
know.
they compared the two? Have they compared that, biased and unbiased and seeing which one is better?
No, this they didn't compare.
Okay.
They just used this approach.
Okay, sure.
Maybe they compared. I
Haven't seen, right? Mm.
yeah, we will see. Okay. Uh, okay. Before presenting results, let's revisit the classical models for comparison. The Black-Scholes model provides a baseline with its constant volatility assumption suitable for simple markets. In Formula 10, you can see the analytical solution for the call option price. There exists an analytical solution for such stochastic process. And for local volatility, it's often that one use the pure formula for volatility. Here you can see. So you can take call option price from historical data uh, and calculate these derivatives of strike price. It's the price uh, it's on what price you would uh, use your option, and T is the time to maturity, time to expiration date.
Mhm.
Okay, and you can use this formula to calculate volatility and use it as a deterministic function.
And why is this formula the right one for volatility?
It's not the right one. It just can be derived from this process.
Well, hold on. For this process, you have to define your volatility. This is Langevin equation, right? So for there, you have to specify what the sigma is, and then you can solve it. But your first equation there says that here's what sigma should be. Um, in effect, below sigma is a function of st and t. Above sigma is a function of k and capital T. So there's something not clear.
You have this
Stochastic
stochastic,
process. Yeah,
yes, stochastic process, and you have corresponding Fokker-Planck equation.
you do, yes.
Yeah, and
But sigma is a
use.
fixed function in the Fokker-Planck equation. It's not, you don't solve for it.
I mean, you can use this in derivation of sigma uh, because um,
Maybe there's
because
some other reasons that go into like specifying what sigma is. It looks like some second order equation for C. What is C?
C is a call option price.
Call option price. Okay.
Yeah,
What is what
it
is
is
capital T and K?
it's like this.
Oh,
It's
stake
call option
price and
price.
maturity. Okay, fine. Maybe there is some other theory that describes why the sigma should have the form it has.
Okay. Um, and the last one is history models. I told about this at
Yeah.
the start. Yeah. Okay. So here is neural network models. The first one is neural network local volatility.
Hmm.
So what they do? They have a neural network F, and the outputs of this network output of this network is call option price.
Mm-hmm.
It predicts call option price. And this price used in this Depure's formula to get volatility. Then by this stochastic equation, they generate paths with Monte Carlo simulations and get model generate price.
Mm-hmm.
But in these models, optimization over stochastic differential equation is not performed. We compute loss function as we did as we always do. We we have output of a call option price and compare it with true price on the market.
Mm-hmm.
So here's like two steps of getting call option price. The first one, you get call option price from model, and the second one from Monte Carlo simulation of stochastic differential equation. Okay.
Mm-hmm.
The second neural network model is stochastic differential equation neural network, and it again predicts call option price, and it again used in Depure's formula to obtain the local volatility. And then this local volatility is substituted into the stochastic differential equation for simulation in optimization via unbiased stochastic gradient descent. So here they optimize parameters of neural network using not the prediction of neural network, but use the expectation value that was getted by Monte Carlo simulations.
Mm-hmm.
The third model, same as above, but the drift term is modeled by a neural network, so it is just the second neuron in the network. And the last one is a two-dimensional neural network that have 5 outputs, and each one for term of this system of equations. So this network generates 2 drift terms and 2 volatility terms.
Mm-hmm.
And again, it used to simulate prices with Monte Carlo and get expectation value of payoff and calculate the unbiased gradient. Okay.
So the covariance matrix for this WTS and WTY has a non-diagonal term proportional to rho. That's what it means. Yes. And then some diagonal terms that I'm trying to understand what
I think that it's like you have 2 stochastic processes, but you have correlation with
yeah, but introducing correlations, they're not going to be Brownian motions, each of them. You would have to diagonalize the covariance matrix to get 2 Brownian motions out of them. But I guess what you're saying is that you start with the desired covariance matrix of these 2 random variables, such that on the off-diagonal terms there's a row, which you can of course do by. So you can start with 2 independent random variables and then make them dependents with the correlation row, covariance row.
Okay, now I will show you the numerical simulations. Just
Mm-hmm.
wait, I put this on the screen for on the screen. Can you see it?
Yes.
So what did they do? On the left, you can see models, on the right, results. So the first one is intraday out of sample prediction. They take the call and put contracts at the same strike price and maturity into pairs, and then 80% of option pairs are randomly selected for the train set, and 20 of the option pairs are selected for the test set. So it means that they do not predict on the next time step, but out of samples in the group of one timestamp.
Oh, so they are not time ordered, you mean those two subsets, right?
Yeah. And here table.
But is this right? I mean, you don't want to use
No, I mean you have option. You have two options that have and two option prices that you got in the same timestamp, and you use one option price to predict another.
at the same time.
Yeah, at the same time.
Okay, I see.
It's the first experiment. And in this table, you can see that the two-dimensional neural network model outperform all classical models, and these neural network models that used the Peirce formula for each date and for each date and for each type of options. But it's interesting that it's different for call option and put option. As you can see here, we can imagine that call option is a long and put option is short, and results for short and long differ very much. Okay.
But you use the same model for both, right?
Yeah.
And so which one performs better?
Call option performs better.
Okay.
You have better metrics. Okay. Here again plots that neural network, two-dimensional neural network works better than.
So what are the x's there? I cannot see.
Axis, yx is option price minus market price, so it's error. And on the x you can see strike price. So it's different type of derivatives. Different type of derivatives have different strike prices.
So how is okay? I guess I still don't understand what are the three lines there?
On the y, it's error of predicted price and the option price on the market. And on the x, it's different strike price for different options. It's different derivatives, but these derivatives options have the same underlying asset. Okay.
So
And
which one is better? Is it the one that up?
no, we want this graph to be zero error. We want best.
Oh, I see. Okay, now I understand. Okay. So it's the different. Okay, so the neural network is closer to zero, and that's why it's better. Okay, now I understand.
That's why it's better. Uh, here, sorry. Here you could see the next day prediction. So they trained on contracts at time on day T and test on day T plus one, like in real trading. Yeah. And again, two-dimensional neural network model much better than classical models.
So what percentages illustrate here? What do the percentages describe?
Its percentage here is relative mean absolute error.
So the smaller percentage, the better again.
Yeah, smaller percentage the better.
Okay.
But it outperform classical models, but two-dimensional neural network here does not outperform like this stochastic differential equation neural network model, because here percentage is higher than here. But like on the other date, it's lower than here.
Okay, but stochastic differential equation neural network model, meaning that there is only one dimensional stochastic process that is being modeled,
Yes.
right? And for the two-dimensional, it's two stochastic. One is the yes or
yeah.
no?
Yes, yes.
Okay. And have they tried three stochastic process? I don't know. I'm just guessing. Like,
They didn't try it.
but have people been looking at the?
I don't know really.
Or maybe all that is irrelevant. All this higher
I
water.
don't really know.
Okay.
The last section is about train on call option, like long, and test it on short and put option. So we can just see that here metrics are much worse than when train on both call and put option. So we can't train on call option and predicts well put option price.
We cannot.
We cannot. Yeah.
Yeah.
We cannot. The next plots are 3D plots about option price, maturity date, and strike price movements. They're not really, these plots are not really useful, but you can see here dependence between option price and strike price, and you can see what is called volatility skew or volatility smile, that option price changes with strike price. Here you can see it better, like smile. Okay, and on these plots, in this paper, it's evident that neural network models are just better than other models, and that's all. They're not very useful here. I won't show. I go back to presentation now. The second method for optimization is partial differential equation approach. Imagine you want to optimize other loss than mean squared error. So your target function would look like this in formula 14. And to get model generate price, you can't use like no, two calculate, it would be difficult to calculate gradient using gradient of this function, loss function, that can be very difficult using Monte Carlo simulations. And they offer another way. You can solve Kolmogorov partial differential equation, or what's similar Fokker-Planck partial differential equation. It can be shown that this two-dimensional process in formula 13 can provide this type of partial differential equation for price of option. Like you can use the same approach that used in each lemma, or use Feynman-Katz equation to get this type of partial differential equation. And they say that you can solve it to get model generate price.
Is there a typo in equation 15? Mu sub y should be a function of x and y, yes? There's no s.
Sorry, yeah, x and y.
Okay.
X could be price here, so I just...
Sure.
Okay. And you can... this equation can be numerically solved using finite difference methods, and then optimized over using automatic differentiation to minimize the objective function G. And there are also two types of options. The first one is American, when it can be exercised at any time up to expiration, and Bermuda option that can be exercised at specific discrete times. I remind you that European option can be exercised only at expiration time. And here you can see again these nonlinear partial differential equations. And it can be solved step by step from time of maturity t, it's here, to now, to t equals 0, because you know the pair of function at the time of maturity. And for American and Bermuda option, you have two options for your option. You can hold it, or you can exercise it right now. And hence you get this relation for expectation value of pair of function. Okay. And they use this approach to evaluate Bermuda and American options using their models. So their models, neural network predicts drift terms and volatility terms. They are put it in this equation. Then they solve it and get a model generate price, and use it in this loss function to update model parameters with gradient descent, stochastic gradient descent. Okay, now I will show you the results. I forgot to mention that for European options, they also have recalibration. It means that they on each day t use model from t-1 and train the model on the training data for day t. So they recalibrate model each day. And here you can see that with recalibration, they have better values of metrics. Okay, let's move to numerical results for American option. They didn't mention in paper what is two-dimensional Houston model, so we should just ignore it, I think.
Mm-hmm.
But for two-dimensional neural network model, it has better performance than classical models, but not as much as it was for European options. Again, the two-dimensional neural network do better than classical models. And next day prediction here, again, two-dimensional neural network model predict price better than classical models. Yeah.
Right.
So in the end, I would say that it can be useful to use neural network model to generate stochastic process to get prices in market.
Mm-hmm.
That's all.
Perfect. Thank you, Vladimir. Super questions. Certainly a lot of information, so guess we'll get back to you with questions. Thanks a lot, and thanks everyone for coming. I'll see you next week.
Mhm.